All right, let's start with a little review from yesterday. So we talked about basically three types of electrical properties at one point. Don't what? Talking to me. All right, so we had three types of properties, three properties. And do you remember those properties?
Yes, conductor.
All right, conductor. What makes something a conductor? Has
free electrons.
Okay, it has free electrons. How can we figure that out?
By the number of shells.
The shells.
And electrons per shell.
Electrons per shell.
Has less than half the allowable.
Yeah, has less than 1/2 the allowable. Allowable. Valence electrons. What's a valence electron?
The outermost shell.
Hey, the outermost electrons. How did I figure out how many electrons can go in each shell?
2 squared.
Okay, so conductor has less than half the allowable. Now, if I said that copper has 2 in the first ring, 8 in the next, then 18, then 1. How do I know that?
You just do.
What's that?
You just do.
I just do.
You took chem.
Copper.
Okay. All right. So it's a very simplistic way of doing things. In fact, that actually is Bohr's theory, where he used shells. But if you actually get into the periodic table, it's a lot more complicated with probabilities and where things are. Schrödinger's. So we're just going with the very simple stuff, because that's all we need to do. So how do I know that? Well, it's because I looked it up and I told you. That's all. So we're not getting into all that, but it was just used as an example of why that is a conductor. All right. So conductor. What else did we have? Insulator. Okay, I'll put insulator here. And before I move on to insulator, what were some other examples of a conductor? Gold, silver, aluminum, a lot of metals.
Aluminium.
Okay, insulator. And what made something an insulator? Okay, has more than 1/2. Valence electrons. Well, that just went away. Where'd you go? There you are. Valence. All right, electrons. All right, and then the last thing was semiconductor. And it's in between the two. We're going to talk about that in a few weeks. All right. We had units of electricity. Units of electricity. And what are those units? Current. All right, we'll start with current. And the symbol for current is what? Symbol is I. Okay. What does the I stand for? Intensity. If you care, it originates from the. Who speaks French?
Je parle pas
Steve. Did we actually get a joke out of Steve? Whoa! All right. All right. Some phrase intensity di corrente, or in English, current intensity. What is it measured in? Okay. What is amps? Where do we get that? Amperes. That is correct. It's short for ampere. Where do we get ampere from? Someone's name. Exactly. Some French guy. Andre Marie Ampere. So
He's on the dead white
that's
guy
true.
test, right?
What's that?
Is he on the dead white guy test?
I don't want to disrespect him. So that's why it's a capital A, because it's after a person. So, all right. And let me think. What do I want to say? And that, what can we describe amps as? We had to describe it.
Flow of electrons.
Oh, I like that. Flow of electrons. Flow of electrons through what? Through a conductor. Flow of electrons through a conductor. If I wanted to use a water analogy, what could I say?
The size of water.
What's that?
The width of the hose.
Would it be the amount flowing?
Mount flowing, like water over a water wheel, something like that. Let me see. What else can I say? B, C, D. 1 amp. 1 amp. Got to be capital A. 1 amp is the rate of flow of 1 coulomb per second. And you're going to say, what's a coulomb?
What's a coulomb?
That's right, 1 coulomb. One coulomb equals 6.28. What is 6.28? What's interesting about that number?
2 pi.
It's 2 pi. That's how I always remember it. It's 2 pi. 6 times 28 times 10 to the 18th. So that's how many electrons are going to flow in 1 amp in 1 second. So it's a rate of charge. All right, so that's current. Let's talk about voltage. Voltage. What is the symbol?
E.
E. E is the symbol. What does that mean? E for what? There we go. EMF or EMF or electromotive force. I've heard it said, and that's what it actually is. You could think of electron moving force. It's the force that moves the electrons. Measured in volts. Named after who? Alessandro Volta.
That's a dope last name.
What's that?
That's a cool last name.
I know.
Close enough.
Electrical pressure. So it is electrical pressure. What else do I always say it is?
Electrical potential.
Yep, difference of potential. So, exactly what do I mean by difference of potential? Well, if I were to draw a battery, and I did, and I have a wire, and then I have a resistor, and then we'll just ground that out so I have a complete circuit, and we'll say this is a 6-volt battery. What's my voltage drop across here? So I take and I put a voltmeter right here. What's a voltmeter going to read? 6 volts. What's the voltmeter going to read right across here? Well, all right, that's 6, that's 6. Why does it read 6 here and here?
Plus 6 and then minus 6.
It's absorbing all of
It's the only
potential
voltage drop.
difference.
It's what? It's
It's dissipating all of the potential difference.
okay, it dissipate. So between one side of the resistor to the other, it dissipated all of the energy. Between one side of the battery to the other represents all of the energy. So it's the difference of potential between the two. What if I were to put a voltmeter right here? What's it going to read? Why would it read 0? There's no potential difference. It reads the same. So I don't know how else I can really describe that, but that's what I mean by potential difference. Now, if this actually read something, let's say it read 0.5 volt, what does that mean?
You have a bad wire.
A bad wire, or more appropriately, yeah, it would be bad. I wouldn't think it'd be a good wire, but a what? There's some resistance in there. It's dissipating some of the, I don't want to use the word power, but it is losing some of the voltage. So you're reading that difference. So somewhere between this point here and this point here, you're actually losing some of the voltage per se. So that's what I mean by difference in potential. All right.
So
Yeah.
That voltmeter won't read 6, right? Against the resistance in the series.
Right. This one right here won't read 6.
That one.
This one. This one.
Yeah.
It'll read 6 because there's only one resistor. If I add another resistor,
Okay, got it. Okay.
that's going to change. It won't be 6 anymore. It'll be something else, depending on what the resistance is. All right. Difference in potential. So 1 volt will drive 1 amp through 1 ohm. Who said that?
You did yesterday.
I did, yes, yeah, thank you. That's all we need to know. Just Kevin said that. Whose law is that?
Ohm's Law.
Do you just say my law?
We don't pay a lot of attention to him. It just encourages him, please. Then we have a resistance, which is the symbol R, which stands for? Pretty brave of you to think of that. But you'd be right. Measured in. Okay. Measured in ohms, which is the omega sign, or Lululemon if you prefer. Named after
Ohm. Sure.
George Simon Ohm. Sir, I'm not in the British monarchy.
Sir Elton John.
Yes, I don't acknowledge that. Resist the flow. What does it resist the flow of? Does it resist the flow of voltage? Why not?
Voltage is not a voltage is pressure.
Because voltage is pressure, not flow. So if I say flow, I must be talking about
Current.
amps, or current is good. All right, resist the flow of, well, actually current is a better word there. Causes, what does it cause the voltage to do? Drop in voltage. It could be thought of as electrical friction. Electrical friction. All right, then we talked about a simple circuit. And I say it must contain 4 things, and they are?
Power supply.
Okay, power source.
Conductor.
What can I have for a power source?
Battery.
Battery,
Generator.
generator, alternator. What's the difference between a generator and an alternator? They both, you can have an AC alternator or a DC alternator, AC or DC. We're going to talk a lot about generators and alternators in the last few weeks. Generators can make DC, and they convert AC mechanically to DC. An alternator converts, DC alternator converts AC into DC electrically, not mechanically. Where are we here? Okay, power source. What else? Conductor. Conductor is a, what can a conductor be?
A path wire.
Okay, wire. I'm looking for, it is a path, correct? A wire. What else? Why, I'll tell you right now, 50% of all the conductors in an aircraft are not wires. 50%.
Airframe.
The airframe. The wire, the airframe. Why did I say that? Well,
That's the ground.
well, we call it the ground, but really all of the electrons are coming out of the battery. They make a short, in my airplane, it's about that far from the battery, to have a cable about that far that's bolted to the airframe, and then from there, all of the electrons go all over the airframe, and they find another ground path and go up. Like, let's say, for instance, the light, my landing light. So That's really a bad example, but you don't know that. So the electrons go all over the place, and then I got a little short wire that goes from the airframe to the landing light, and they find that pipe, they go right up in the landing light, then they find the positive wire and go positive wire all the way back to the battery, right? In reality, that's the way it works, right? And why was my example a bad example?
Because you're using conventional.
No, that was electron theory flow.
Oh.
Goes out of the battery into the air.
Right.
Because my cowling is fiberglass and it doesn't travel through
Oh.
fiberglass, so it means I have to have a much longer wire than that. So, but almost a good example. All right. Okay, so conductor, wire. What else do we have?
Load.
Okay, we have to have a load. What if we don't have a load?
Until the short.
Okay, no load, no load. Wait, I think I heard a good answer. What was that? I heard
Something's burning.
something's burning. Yes, no load equals burning. Burning. Smoke. That's a short. We don't like that. I mean, all of us in here. A short is a bad thing. So you must have a load, or the wire gets very melty. And the last thing we need is need a complete path. That's the purpose of the switch, to open the circuit and close the circuit, to complete the path or not. Okay, we have Ohm's Law. Which is expressed as E, I, and R. And there's many other formulas that go in there, but that's the one that'll get you through. And you have the, hang on, pause. All right, that's everything you need to know about electricity.
That's it?
That's it right there. It's explained in detail. Am I wrong?
So do I need to draw that on the test?
You do need to draw this on the test. You'll be graded upon that. All right, there's all the formulas for Ohm's Law. And when I say it's E, I, and R, I'm simplifying. There's E right here. E is I times R. So I'm basically telling you it's this one. I is E divided by R. I is E divided by R. And R is E divided by I. So right there. So we're only using those three. And then I say we have power, which is the formula is what?
Pi.
Pi, remember? Who likes pi? P equals I times E. So power, there we go. So we're using those four. But there's all these other ones, and if you have this little wheel, you can do that. But I'll be honest with you, in that I don't see as far as I shouldn't be recording this part, but as far as the FA test goes, as far as my test goes, as far as even being in the industry, I've never had to use these other ones. I'm just fine with what I have right here, and I can remember that and work with it, and I have no problem with that. So everything seems to work just fine that way. Okay. If I'm wrong, then I'll correct myself next class. And
It's not like it's not recorded.
I know. All right. What's next on there? I don't even know. Oh, resistors. Who cares? Alt tab. We want to go back to that one. There we go. Okay, so Ohm's Law. There's our Ohm's Law we talked about. Okay, so in addition to that, we have power, which is what?
P equals I times E.
Times E. And what is power? What unit is that expressed as? Huh? Okay, so power is expressed as watts. Watts. Named after? James Watt. And the formula is, guess what? E times I, because it's power and watts is the same thing. Power and watts. All right. And let me think. There's something here about what a watt is. Yeah, we'll circle back around to watt. Watt? So, back to Ohm's Law. Ohm's Law says, boy, I hate to write this. The current in an electrical circuit is directly proportional to the EMF and inversely proportional to the resistance. Did you catch that? Hey, the current in an electrical circuit is directly proportional to the EMF, which is the same. The EMF is the same thing as what? Okay, voltage. So before we move on, what is that saying? The current is directly proportional to EMF.
So you increase the voltage, you increase the current.
Okay, I like that. PK had it right. If you increase the voltage, or an increase, we'll do that, and increase in the voltage will increase current flow. That's what that's saying. And the rest of that is, where was it? EMF, voltage, and inversely proportional to the resistance. What is that saying?
That if you have more resistance, you have less voltage.
Okay, as resistance increases, oh, you get,
Less current.
thank you. As resistance increases, current decreases. So current, if I increase the voltage, current does what? Increases. I increase the resistance, current goes down.
No.
All right. And I think I wrote this one yesterday too. Ohm's law is 1 volt causes 1 amp to flow through what? 1 ohm. Okay. 1, 1, and 1. What if I make it 2? Oh no. All right. Back to power. So power. Power is expressed as what? As watt. Express it as P or W. The formula is pi. P equals I times E. It is 0.00. No, I'm not going to write that because I don't need you to remember it and I don't want you to confuse you. 1 watt equals 1 volt times 1 amp. Volts times amps. Yeah, I'm just going to tell you this. It equals a certain amount of horsepower, and to be honest, it's 0.00134 horsepower. And I want to tell you about horsepower because it's kind of relevant. And I don't know if I'm going to get this story completely accurate, but this is a true story. I know I lie to you all the time, but this one's actually true. So, with my made-up stories. So, and when you talk about horsepower is, who knows what kind of horse it is?
Drive horse.
A what?
Like a horse.
A specific type of, no, not a
Flagstaff.
It's an English workhorse. So it's actually based on an English workhorse. And as I understand it, which means like this could be full of crap, but I actually believe it, is that, and it'll come to me who actually made it, James Watt. So I believe it was James Watt who actually had this problem. He created a steam engine. And he wanted to sell the steam engine to the mining companies, and they were using horses to do something. I don't know if it was, going in circles, running a pump, or some strange thing.
Drive coal out of mine.
Yeah.
Okay, so you're with me on this, but I also thought they did something. Anyway, so he wanted to sell the steam engine, but you have to relate this to that, and he couldn't sell it, so he came up with the formula of this is a horsepower, and it was how much work one English workhorse could do, and then he had his particular engine, which was then measured in horsepower, which then was measured and translated into watts. I think I kind of screwed it up, but anyway, that's kind of how it came about. So there is an absolute correlation between watts and horsepower. 1 horsepower equals 746 watts. And that's not something you necessarily need to memorize, but you're gonna use it a lot. And so you're probably gonna end up memorizing it one way or another. And it is defined as the amount of energy needed to raise 550 pounds a distance of 1 foot in 1 second. Which then brings you to the term joule. And that is work done by 1 watt in 1 second. Now I want you to know that, but I'm not going to ask you on a test like what does 1 watt equal or what is 1 joule. All right, that's, I don't know, don't need you to have that memorized, but we're going to work a lot with this stuff. Now, how about the dangers of electricity?
It'll kill you.
All right, dangers of electricity. Well, it's not very dangerous if you ask me.
Not on the 6-volt battery.
Not on a 6-volt battery. I'll leave that there. I'm going to move it over in a minute. Okay, so one of the jobs that I had, one of the jobs that I really enjoyed the most was I did a lot of non-destructive testing work using a magnetic particle machine. And as I mentioned before, you basically take a crankshaft or some component and I will put current through, like we'll say a crankshaft, I'll put current through it and I'll turn it into a magnet. And then I'm going to show you all this stuff. We get our machines working next semester, how that works. We'll talk about that. But so I'm putting current through the crankshaft. Can you guess how much current you put through a crankshaft?
A lot.
Oh, what's a lot? 100 amps? 200 amps?
You tell me.
Well, I tell you, in the neighborhood of 3,000 amps. So my particular machine was quite lengthy, and it has a bar that would run across the front with a little thing that would hit a button. So all I had to do is I put the crankshaft in, step on a button, these rams would go in and hold it, and then I would put the, call it the juice on it, but flow the fluid across it and just lean into it. My knee would hit a bar and would energize it. Well, as would always happen, I would be in there working, it's dark, because that's all under a black light, and behind a curtain, and the boss or somebody would walk in as I'm putting the crankshaft in, I've just stepped on it, the things are coming in, they come in to lean in, what you doing? And there's 3,000 amps, so I'm hanging on to the crankshaft at that time. How did I not die?
You were right on voltage.
Well, I did. No. What's that? There's no voltage. There's no voltage. In fact, I even had a conversation. We bought our new machine. I don't know if you guys have even seen it over there. In fact, I need some help moving it. And I asked Magnaflex, I said, hey, by the way, how come it's safe to hang on to something where that many amps are flowing through it? I said, well, first of all, the voltage is so low, it can't break through your skin. And the parts that you're working with are so, the resistance is so low that it doesn't see you. It doesn't work that way. Now, I will tell you this, though. Camshafts are the worst. I don't know why, but they have a little coating on them or something. But you put it in you put it in the clamps, and sometimes you wouldn't get good contact. You hit the button, and it will arc across and shoot out at you. It arcs, and whoa, make you jump. So there's enough voltage to jump that, I guess. Anyway, so dangers of electricity. I'm going to move it over here. So, all right, so I didn't get hurt with 3,000 amps. So that's sort of the problem with when some say, well, it's not the volts that'll kill you, it's the amps. Stun guns. Does anybody have any experience with those? I mean, you seem like a guy who's running with the law a few times, Dennis. You been tased?
Actually, no. I've been based.
I have. It hurts.
You see, I only pick on the guys that really don't think this happened to. I didn't know, but of course. Yes, and so it's how many volts? Anybody know?
Like
Maybe
50,000.
up to, maybe up to
50, 50,000, 100,000. So what powers that thing? I mean, they must be dragging around a car battery, right?
No.
No.
9 volt.
It's a 9-volt battery. Wait, how did you get 50,000 from 9? Okay, it's transformers. It's step up. Now, you can't create energy from nothing. So we'll talk about transformers in a few weeks. But basically, you take voltage, and every time you step up the voltage, you lose amps. You trade amps for voltage. So it gets all the way up to 50,000, 100,000 volts. And what happened to the amps? It's nearly non-existent.
Milliamp.
So when somebody says things like, well, it's the amps that'll kill you, not the volts. Yeah, I don't know. I still don't want to be zapped with no amps and 50,000 volts. Thank you very much. But it is true. So remember this. So my story about why didn't I die? Well, your body, or mine too, has a lot of resistance. What's that? Yeah, it's dangerous stuff. So remember, I'll write this. So remember. Not that I want to push your luck on this. It takes more than a few volts to cause current to flow. So if you don't have any voltage, current's not going to flow. But you get enough voltage going, and oh yeah, it's going to hurt. So callous, dry hand. I don't want to write this. Well, callous, dry hand. How many ohms do you think that is? Well, first of all, you guys probably are all soft and don't have calloused hands.
What?
Unless you're a fueler.
You wear gloves. Get out of here.
This is a working man, either which way. May have more than, so greater than 100,000 ohms. Because you have a thick layer of dead skin, believe it or not. Internal body. Internal body has about 300 ohms. It's not much. So once you break through, it flows a lot easier. So you don't want that to happen. All right, so 1 milliamp, 0.001, if you're not familiar with that. You can feel it. It has a little tingling. What is that? Where can you experience that?
9-volt battery on your tongue.
Yeah. You seem like a battery licker. Sorry.
I've done it. I don't know how many times.
Me too. I dare the kids to do it, you know. Now try the car battery. Okay. 5 milliamps is accepted. Oops, as the maximum harmless current. And this is all according to Google.
Because we are usually mechanics.
10 to 20 milliamps. Muscular contractions, the inability to let go.
Does it say accepted of?
Accepted as
Oh.
the maximum. So I started to write something else and I made it as. Muscular contractions. Muscular contraction. You can't let go. You're there. You're hanging on. It hurts. Well, why don't you let go? I can't. All right. We're still in the milliamp range. So 100 to 300 milliamps. Can I just write VFib? Everybody knows a VFib. Come on, you guys watch doctor shows, right?
What?
What's VFib?
Ventricular fibrillation.
This is like you and your quick question. Well, it takes longer to explain that one. Ventricular fibrillations. Your heart.
stops.
Well, that's
Oh, it's well.
it flutters and is absolutely worthless at that point. So 6 amps
You need to grab onto it again. in other words.
You said,
6 amps, sustained VFib, followed by normal, or followed by, sustained, we'll say, that's not right. Temporary respiratory paralysis and possible burns. So that's bad. Very bad. Yes.
So when your heart stops and the EMTs use the
Hmm?
shock thing,
Mm-hmm.
would be an amperage going through you to get your heart going again, right?
It's actually registered in joules, in watt seconds. And so I don't really know what the ratio of amps to watts is. I think it's a lot more volts. We should try one. How come we don't have one of these at
You know
school?
what? I bet you we should.
I know.
We need to get
Try
one.
it out.
We may have one in the.
Brett.
That'd be
You gotta look the battery first.
Yeah.
I'll tell you.
All right. So be careful with that. But speaking of amps, how many amps do you have in your little 6-volt battery?
Not 1 million.
because it tingles.
It doesn't say, does it? No. And a lot of batteries will say on it the amp hours, which is how many amps per an hour. But so if I want to know how many amps are in that little 6-volt battery, couldn't I just take my amp meter and put it on amps and just touch the things? And it would
Do it.
Yeah, then
Do
you're
it.
talking to James.
It was sure.
Steve.
Does that work? Anybody experienced that or tried that?
It'll work for a split second.
Not even that long.
A split second is a very accurate. What's the matter, Alex? You look a little sheepish over there. That's okay. It happens. You're not alone, man. That's the whole point. You're not alone. So what happens? So for a split second, it will register the amps. Well, how many? All of them. It's all of them. And if you blink, you're going to miss it, and then it just pops the fuse, and then it stops working.
You gotta retry.
Then try it again.
Maybe you'll catch it one time.
Yeah. Maybe, yeah, just keep trying it.
James, I
Use
promise, this is the
pop,
last
just put some
time. I
aluminum foil in there.
So, okay, so the point being you can't do that because that's a dead short and the fuse inside the meter is trying to protect the meter from that. So don't do that. Let's see here. All right, we talked about series, same requirements and the formulas. Kirchhoff's law number 1. I kept talking about Kirchhoff's law, but I didn't have the right spelling. So we'll do this. I total equals what? In a series.
I1
I1 plus I2 plus I3 plus
I1
equals I2
equals I2 equals
I3
I3. And voltage total equals V1 plus V2 plus V3. Okay. And resistance total equals R1 plus R2 plus R3. There we go. Got it? Yep. This right here is actually known as Kirchhoff's law. Kirchhoff. Kirchhoff's law.
Is there another law?
Number 1. There's a lot of laws.
Yeah, 'cause from the computer, it was saying some other dude's name. Law.
Ohm?
No,
No, it was
it
like
started with the S, right?
Heshoff or
I don't know.
Kirchhoff or something.
I don't know that one.
That's what it was.
This one is the algebraic sum of all the voltages around a closed path or loop. Another way of saying it, the sum of all the voltage drops equals the total voltage source. So voltage source equals the sum of all the drops, which is what I said. All right. Parallel circuits.
What do you mean by number 1? Is that
Yeah, it's just
First
law number 1.
Law.
okay.
Like,
And it's just the voltage part of that?
yeah. All right, parallel circuit. Well, what are the requirements?
Bless you.
What are you, the Pope now?
Multiple path?
Okay, well, you have to have a conductor.
more than one path.
Well, I don't need to write that. Still have a conductor, power source, load, more than one path, or let's see, sorry, current.
Gotta do like
conductor. C-O-N-D-U-C-T. Got to have the conductor. We got to have power source.
All that mumbo jumbo.
We must have a loads. And it must have more than one path for current. All right, so looking back up here, we had series. We'll do the same thing. So I total equals what in a series circuit?
I1 plus.
Well, it's going to be different. I1 plus I2 plus I3 equals I total. Well, that's kind of like voltage for series, right? So voltage in parallel is voltage 1 equals voltage 2 equals voltage 3. And resistance is, okay, now there's 3 or 4 different formulas. And I've always kind of made it a point, and I have it in my notes, but I always made a point to not teach all the different formulas. Why? Because I guess that's one thing I never liked about some math classes. It's like, okay, well, here's 16 different ways to do something. Now I got to remember what, 16 different ways? How about you show me one way and I'll remember that way and get it right every time. So there's a formula for if you only have 2 resistors. There's a formula if you have resistors that are all the same value. And then there's a formula for finding the missing resistor. And then there's a formula that works for almost everything except finding the missing resistor. And so I just go with that one, which is 1 over R1 plus 1 over R2 plus 1 over R3, all of that under 1, or 1 over. And you can use this for every single one of them, except for the find the missing resistor. So if I gave you a simple problem and I said I had 3 resistors and I gave you a total over here, I'm just going to total. And this is X and this is X, but I said, what is this one over here? There is an exact FAA question like this, where they give you the total and this. So you go through all of this and tell you, hey, you're going to have to remember this formula, you're going to have to figure it out, but it's on the FAA test. So that means there are how many possibilities?
3.
There are only 3 possibilities. When I took it, there were 4. So all you have to do is say, well, if it's, let's say they'd say that one's 10, this is 20, and you're supposed to find the missing, and this is, well, it's 30, and this one's 40, and this one's 50. But they give you the total, just say, well,
Work it out.
say it's 5 ohms. All right, well, I'll just put 30 here and try it. If it's 5, I'm done. All right, I know those numbers probably don't add up. Something funny about what I just wrote. I wrote a 10 and a 20, and I didn't have this here, and I said, then it must be 5. Am I losing it? I mean, why would I pick 5?
Because
The
the
total
yeah,
is less
the total
than
is
the
less
smallest
than-
resistor in the circuit.
Remember that. The total resistance is always in parallel is always less than the smallest resistor. So I just got to look for that. So if I would have done something and came up with an answer of 15, would that have been right?
No.
It's got to be less than 10. So remember that when you're doing these problems, always stop and look at it. So many people miss a question. I'm like, all you had to do is look and say, well, it's got to be less than the smallest resistor. All right. So why is it like this? Why is the more resistance I add in parallel, the total starts to drop? I mean, it seems kind of crazy, right? And one of the questions I may ask you when you're doing your measurement, you have your circuit set up with 4 resistors, and I'll say, hey, what's the total resistance? And you'll measure it, and I'll say, what happens if I take this last resistor out? Is your resistance going to go up, or is it going to go down? You have more resistance or less resistance? I have more resistance if I take out a resistor. Well, It doesn't make sense. The best analogy that I have ever come up with is going to San Francisco. You guys,
It's a joke.
no, it's kind of benign. Now, mind you, I haven't been to San Francisco in a long time. Last time I was there, Bay Bridge was like $2, and I asked somebody the other day, and it was like, how much? Seven.
Seven on off peak.
Okay, then there was no. Anyway, we'll get to that. So anyway, you're coming in to the Bay Bridge, and they've got 2 toll booths open at 3:00 in the afternoon. What's going to happen?
Big ass
Everyone's in a
The
farm.
current flow.
Yeah, everybody's-
is
The current flow is going to come to about nothing. All right. There is a lot of resistance to get through. Now each booth represents resistance, right? But I open up a second resistance booth, and what happens? Flow starts to go more. Open up another one, it's still resistance. Flow goes better. So open up all the resistors, and even though it is more resistance, flow gets better. So that you can get to San Francisco and poop on the sidewalk.
Have other people clean it up for you.
Which I hear is a problem there. All right.
Well, there's other people there.
All right, so let me see. Resistance.
Land it on that there.
All right, so and I'm going to put this, and this, it's funny because Tom and I were having a conversation. He goes, oh, make sure you tell them, don't ever say this. And I said, I don't, so don't worry about it. The amount of current passing through each resistor will vary according to its individual resistance. And so Tom's point was, some people say things like, electricity will always follow the path of least resistance. He goes, don't say that. I don't. And the reason why you don't want to say that is because we could look back up here, this diagram. If I have 10 ohms and 20 ohms, and we'll say I have 5 ohms here, what's the least resistance?
5 ohms.
The 5. So if that were true, then all of the current would go this way. Would it go down? No, it would all go this way. Path of least resistance is through the 5. So you have to be careful with that statement, was his point. However, if I put a wire from here to here with no resistance, where would it go?
It's gonna go.
I don't know if there'd be much going through the other ones. They would go through here. Anyway, I digress. All right, I think that is a good spot to take a little break.
And Tim can tell us how he got electrocuted. So Tim.
You dropped something.